Yes, okay.
Thank you. Today's talk will be about a part of this non-contact homology that related to the physics story that I told yesterday, particularly to this topological string. And we will start by finishing off actually the talk from yesterday and discuss large N transitions. And then we will try to derive this so-called augmentation polynomial. I'll tell you what it is from the point of view first of physics, and then from the point of view of non-contact homology. And then we'll discuss how Lagrangian fillings of this Lagrangian co-normal induce augmentations in various ways, and that will actually lead to a kind of a proof of the equivalence of the physics polynomial and the math polynomial. So, and then at the end, I want to discuss what would happen in some other manifolds if you don't have a proud title, but maybe I will mainly discuss RP3. But anyway, so it's some kind of general phenomenon that's interesting. But let's start to go back to what we did yesterday. So the main point that I didn't manage to make was to continue the physics story a little bit. So recall that what we were doing is we were relating, following basically Witten, relating the Gromov-Witten theory, so the open string in T star S3 to the Chern-Simons theory in there. And in particular, we found a relation that expressed the curve count, so this psi of x, that counts the curve. So remember what we are doing, we're taking this T star S3, symplectic manifold, we take the zero section and put n Lagrangians there as serving as boundary condition, and then we have one Lagrangian along the co-normal, and we count holomorphic curves with boundary on this Lagrangian configuration. And then the outcome was that the count actually can be expressed as the Calabi-Humphreys invariant, where the Calabi-Humphreys is given by insertion in the Chern-Simons pattern. So, and now what we are going to keep in mind is basically these curve counts, so not so much Chern-Simons. And we are going to look at it from the point of view of this large N transition. So here we view the cotangent bundle of S3 as a quadric in C4. So we just take the sum of squares of 4 coordinates equal to real epsilon. So then you can see this symplectically looks like T star S3. And now we can shrink the zero section, so just put the epsilon to 0, we get the cone. So that's the thing that's not drawn in the picture. So on the left-hand side, you see at infinity the cotangent bundle of S3 looks like S3 times S2. And the picture is supposed to indicate that the triangle somehow fills in the S2. So then it becomes S2 times D3. And now, when you take the cone, you sort of pinch in at the bottom, so you get radius 0 S3. And now you can resolve it by instead letting the S2 grow out. So this is the small resolution, and gives you the O minus 1 plus O minus 1 over CP1. And the conifold transition relates the open string theory on the left in T star S3 with maybe that's on the next slide. I should show that. So with n copies of the zero section to a closed string theory in Y, so in the resolved conifold, basically saying that if you count these holomorphic curves or the perturbation theory, left, then you get the same count on the right, provided you set the area T of the CP1 in the middle equal to n times GS. So you should think of n as going to infinity and GS going to 0, but you keep the product constant. And then I'll say something about, so this is, I think, not, we don't have kind of proof in math of this mechanism, but it was somehow verified. So this curve count you can basically do, right? You have basically in the conifold, the resolved conifold, there is only one holomorphic curve, this is the central CP1, and then you have to count all its multiple covers, and then you can do it. And that agrees with what you would get from Chern-Simons.
Can you remind me what GS is?
GS is supposed to be this string coupling constant, so it's the genus parameter in the expansion.
Mm-hmm.
Yeah, so it's, that's right, sorry. So that's what we are going to use. So now, in fact, there is a physics proof of this which I looked at, and I think I would like to just encourage more people to look at. It's actually a very nice proof where you define some sort of string theory where half with parts of the surface is in one phase and other parts in the other phase, and then somehow we interpolate between them, and this thing actually grows out. So I think this would be, I cannot say that I understand this from math point of view, but I think it's a kind of would be a great thing if we could. So this should certainly be studied, but at least there is a path integral proof of this kind of mechanism. Now, we are going to continue a little bit, and indeed we are interested in not just the holomorphic curves with boundaries on the zero section, but also the ones which tie to this colored Humphrey polynomial. So they would have one boundary on the conormal. So let me draw a picture again. So what we have is we have this one side, this T star S3 thing, and then we have a conormal here, which somehow goes down. So if you take LK intersected S3, that's just equal to the node K itself. But what we're proposing is to actually take this LK and shift it off of the zero section, so that it looks like this instead, keeping the notation. Now you cannot do that quite with an exact deformation, so we're using a non-exact deformation, and in the simplest possible way. So if you think about the Lagrangian conormal, then it sits over a small neighborhood of K, right, which is just looking like S1. So neighborhood of K is just S1 times D2 in S3. And now in here, you can shift LK along somehow the closed one form, the data which goes along the circle. So that's somehow is the remaining direction in this conormal. So when you do that, you get the non-exact Lagrangian. It's shifted all the way, also out at infinity. But at least you can get it off of the zero section. And in terms of, I'll say something about that later. But once we have this shifted LK, then we can carry it over to the other side of the transition, because transition somehow just has to do with what happens near the zero section. So that means that we get this LK. We can think of it as sitting inside. Well, I'm not going to draw a picture maybe. We can think of it as sitting inside the resolved conifold. So after shifting it off. So
there seem to be two ways.
There are two ways, yeah.
But you just say LKs and Y.
I pick one. So I will have many ways. I will have you can shift it along positive dictator or negative dictator.
Right.
That's right, yeah. So it will enter as some kind of parameter in what I'm doing later. So.
When you say this function, is this the same function as before? Is either Z Gromov-Witten Y LK divided by Z Gromov-Witten?
Yes. So this one, What I want to say is now that this function is now supposed to count. So it's now supposed to count homomorphic curves. So what we have schematically is the following. So first we have this LK sitting in here, and we're counting somehow monomorphic curves like that, which end on the zero section. And then when we transition, so before we said that when you have only boundary here on the zero section, then somehow they close up and we get the closed curve on the other side. Now this LK is far away from the zero section, so following this sort of physics reasoning, following this physics reasoning, so we would say that all the curves, all the boundaries on the zero section close off. So this goes over to the following where this is now a closed curve. So that means that counting, so this was the same as the partition function of counting all the curves in S3. So we have that, and this is the same thing as that. So we're recovering the colored Homfley through such a curve count, basically counting all the homomorphic curves with boundary on LK in the conifold and dividing out by those with no boundary, right? So that's the statement I would like to make. Is it okay?
Now you have a parameter that you didn't have before, which is this.
Yeah. Right. So remember there was this kind of e to the x thing, and this will actually be the real part of that parameter. So somehow now turned on, right? So before there was just basically, it's keeping track of homology class, but now I have this is upgraded in some sense to complex parameter. Before it was maybe just monography along the sheet, but now I have a real part of it as well. So, but the statement should be that with this, counting in this sense, and the parameters incorporated in the e to the x, which basically tells you how much you achieve. Okay. So let's now try to look at the physics way of getting out not the whole information, but the leading term of this wave function. So what we are missing here, in some sense, are we're looking at all the holomorphic curves that end on the zero section over here, but there are of course those which just go back and forth. They go back and forth between the conormal and itself, but those again we can, in a simple way, use again this sort of Witten argument to control. So they basically correspond to a very simple GL1 or U1 Chern-Simons theory on S1 times R2. Now that's if you write up the path integral in terms of these connections, it becomes exactly the path integral of basically a particle in quantum mechanics moving along the line. So it's somehow it's x dot p plus p dot x, where one is one period and the other one is the other period on the torus. So therefore we basically know what we're supposed to do when we quantize this. We're supposed to do what we're taught. We're substituting p for the derivative of with respect to x. And now we can also, this asymptotics formula is maybe the main reason we are here at all. But anyway, so if you do this short wave asymptotics and wave fronts and so on, then what you find is that the leading asymptotics of this thing is given by integral p dx. On the other hand, if you think about this from the point of view of Gromov-Witten theory, then the leading asymptotics are given by counting disks, right? So then after we count disks, we count more complicated curves, and they come with higher powers of GS than 1 over GS. So from this we can somehow conclude that P is equal to the derivative of the disk potential with respect to x. So and then now here's your equation, right? So basically this now parameterizes the corrected Lagrangian, right? So the Lagrangian is shifted with connection corrected by the disks ending on LK, and then we can somehow we can now use analogy with this somehow SYC mirror symmetry. But first I want to note that this actually, if you look at it, it's not so clear, but if you think about the Homfly polynomial, so after all, our wave function, the psi, the full wave function, that's equal to the Homfly polynomial, color Homfly, and that's known to satisfy a certain recursion relation. So basically, it's determined by its first some piece, and in particular, you can write it as a differential equation, if you wish, where the e to the p and e to the x looks like these operators. Okay? And now, when we look at this somehow short wave asymptotics, the semi-classical thing, then what happens is the variables become commutative. So basically, we know that this colored Homfly satisfies some operator equation, and what this should be by derivation is basically the commutative version of that operator equation. So in other words, this parameterization should give us an algebraic curve and then determine a polynomial in e to the x, e to the p, and then kind of deformation parameter q. And then and since this is kind of conference of mirror symmetry, so the mirror of the conifold should now be given by this polynomial equal to uv, where Lk corresponds to the line in the fiber and at point P in this right. Okay? So that's somehow the general story, but now for the relation. So the most important thing here is this polynomial that's locally looking like the derivative of the disk potential. So that's where all this business started by Mina and Gromov-Witten. So the observation that when you calculate this thing, you actually get in examples exactly the augmentation polynomial of node contact homology. And so I would first tell you what that is, and then try to tell you why that is so. Okay, so remember again what we were doing in node contact homology. So there. We have this kind of conormal torus, and again we have this somehow xp homological variables, and we associated to it an algebra, which was the algebra over the group ring of the relative second homology, and generated by Rave ports. So the Rave ports came in they were actually, corresponded to binormal geodesic chords or binormal straight lines of the node. So they came in 3 degrees, 0, 1, and 2. So that was our algebra, and there was a differential on here that counted holomorphic curves. So the differential basically counted some kind of holomorphic curves like this, with one positive end and several negatives. Okay, so that was the DGA. And now, if you think about this, you can think about it as a family of DGAs parameterized by the coefficients. And we're looking at the the locus where we have augmentations. An augmentation is just a chain map or representation of this algebra into the complex numbers, where we think of the complex numbers as a very trivial DJ sitting in degree 0. So the chain map equation is wrong here. But actually, sorry. So it says that this should be equal to 0, right? So because there is no d on C, so it should be equal to 0. And now, oops. And we define the augmentation variety to be the algebraic closure of the locus where we have such representations. Okay, so let's think a little bit about how that works and what it may be. So remember that in general we had the formula for this differential. Non-compact homology. Let me just say something. So in our when we represented the knot as a braid around the unknot, then we had somehow generators Aij, Bij, Cij, and Eij. These were of degree 0, this degree 1, this degree 1. This was degree 2. So now we'd like to have a chain map. So we need to make sure that the image, so the chain map is degree preserving, so we should assign some numbers to the degree 0 generators. And basically the only thing we need to do is we need to look at somehow dBij and dCij. So that's equal to some polynomial in Bij in the coefficients and then in the Aij's, right? So it's a non-commutative polynomial because we have a non-commutative algebra, and these also some polynomials like that. Okay. But now we're looking at maps into complex numbers, so in fact we can completely forget that this is non-commutative, right? So we can just view these as some kind of commutative variables, and we're looking for the locus where in terms of coefficients, where these all have a common root, right? So this is a kind of problem in elimination theory, and what we find is that we get by doing the elimination theory, we get an algebraic set. In fact, it's a curve in there where we have augmentations. And the polynomial of that curve is called the augmentation polynomial. And the thing that I'm going to prove in a while is that this local P is equal to the derivative of the least potential that actually parameterizes a branch of this augmentation curve. So, but let's first maybe look at examples. So remember, this was the one calculation we did. So for the unknot, there was only remember that there was just this ring here called 1, and then there were two variables C and E. This was degree 1, this was degree 2, and D of C was equal to exactly the expression here. So the augmentation variety is immediate, right? So it's just this has to be equal to 0, and then we're done. For the trefoil, we also had the differential there, and then already here the polynomial is getting slightly more complicated, but it's not so bad. So you have to eliminate two variables, a12, a21, and that's certainly doable from what I did before. But this is just to kind of give you some flavor of what it may be. Now, let's first look at what we can say about augmentations if we look at Lagrangian fillings in T star S3. So in T star S3 we first cannot get somehow the whole theory because the Q variable somehow is killed. Now, in T star S3 the S2, which represents this thing, we have to put Q is equal to 1 because we cannot somehow, when we look at holomorphic curves in there, we cannot find this homology class. And so the standard picture from symplectic field theory is that if you have a Lagrangian filling, so in particular we have Lk sits inside this T star Sk, so that's an exact Lagrangian filling of lambda k. So such an exact filling does induce an augmentation as follows. So what we're doing is we define a map which counts holomorphic curves of the following form. So at infinity we have the asymptotic of the rate course. So I want to compute epsilon, the augmentation acting on A. So at infinity, it's asymptotic to my rate chord A, and then it stretches down along Lk, so it has its boundary on Lk, and then it sits inside T star S3. So all of it is inside T star S3. And we would like to say that now this count, which is a count where we can incorporate the variable e to the x, right? E to the p needs to be 1 because p is the meridian, and when I take this Lagrangian filling, then p is filled. So there is no more homology variable in there. It's killed. So
for that particular.
For this particular one, e to the p is 1. So when I take the conormal, so it's the conormal of k. So this particular one is killed, and then I would like to show that this is a this is a chain map, so it satisfies this equation. Well, in fact, that's the standard SFT argument. So what I'm doing is I'm looking now at the corresponding moduli space, but of dimension 1. So I'm looking at the corresponding moduli space of dimension 1, and its boundary will consist exactly of broken configurations of the following form. Where you have 0 disks inside the T star S3, and then at infinity flows off an OR invariant family of disks, right? So this is exactly D and this is epsilon. So the contributions to, sorry about this. The contributions to epsilon, the boundary followed by epsilon, is actually in 1-1 correspondence with this boundary of a one-dimensional moduli space, and therefore it is 0. So what we learn from this is that if I set q equals 1, then e to the x, e to the p minus 1 is a factor of the augmentation polynomial at q equals 1. So e to the p minus 1 divides. Right, so that's what it's saying. So we're actually here not doing very much. We're just looking at the coefficients, and we say that if we set e to the p equals 1 and q is equal to 1, we have an augmentation. So therefore this divides the polynomial. So now we can actually see the same thing for e to the x. Namely, if you think about the conormal, so here somehow it's this S3, and then there are many ways to see this, but let's pick one. This is Lk, and this is K. So near the zero section, in fact, the intersection looks like this, right? This is kind of, I'm dropping some dimensions. So you can smooth it like so. So basically, what you're doing is you're drilling a hole, and so you find another Lagrangian, exact Lagrangian filling, which has the topology of the knot complement. And in particular, in this filling, the longitude x, right, is killed. And so it's also the case that e to the x divides this augmentation polynomial. And in fact, you see that for the unknot, this is it, right? This is the only factors of the augmentation polynomial. Whereas for the trefoil, you have a little bit more. And
Tobias,
yes?
is it really e to the 3p, or is it e to the 3p, e to the x, or something like that?
I think maybe maybe some kind of change of variables, but I think it should be correct.
Okay,
I think
because that factor is divisible by the previous one.
this factor is divisible by. If somebody knows the A polynomial. Okay, so maybe I'm wrong. I'm sorry. It may well be that I'm wrong. If somebody knows the A polynomial of the trefoil, then we can soon figure out. Okay, maybe I'll have to check. I'm sorry.
So in the trefoil, kind of this last factor is corresponds to 3 fillings, right?
Huh?
Does this last factor for the trefoil correspond to 3 different fillings, or?
No, it doesn't. So it corresponds to the complement filling with certain flat connections. I will explain how they arise. Actually, all of them. Okay, so in fact, as I will try to, so we'll see how it works. But anyway, in fact, looking at these fillings, in particular the complement filling, you can actually explain the whole augmentation polynomial for q equals 1 in terms of the knot group, or representation of the knot group. So the upshot here is that one can actually compute the degree 0 knot contact homology in terms of the fundamental group of the complement. And the result is the following: that this will be a module over the meridian and longitude classes, and it's really generated by these elements in there with the following relation. So the E is the trivial class, so that has to be set equal to 1 minus e to the p. And then longitude and meridian behave, as you would guess. And then there is a third relation, which is a little bit non-trivial. So maybe I'll draw the picture of what's going on. So one way of understanding this is actually looking at this string topology expression for the non-contact homology. So let me at least show the picture of this concept. So the idea here is that you use this LK and you use this kind of S3. And now we look at holomorphic curves of the following sort. So on the top we have again A, and then we do the following. So first we follow LK, and then we do kind of Lagrangian corner and follow S3, right? So it's a DC holomorphic curve like that, right? So you can switch Lagrangian at the corners, and then you have LK, S3, LK, S3. So basically now what you can do is for each you would like to define some kind of chain map like this. And what are you mapping into? So for each chord, you associate to each chord a kind of a chain of strings like that, which somehow goes, it's a path in S3 and then a path along the LK, and then a path in S3 and a path in LK. So on this side, you would now like to define some differential which mimics the differential in the non-contact homology, and then by this sort of this tribute strips would get some isomorphism. Okay? So, but what does that differential have to take into account more than the usual things? Well, the differential, call it maybe B, is certainly has to include the singular differential, right? Because you can go to the boundary where you just split off, and that's the boundary of the chain, actually. But then you have two other operations, which we call, this is in joint work with Lenin, Kajt-Silebak, and Jankolashev. So there are two other operations which we call delta Q and delta N, which corresponds exactly to, you know, what can happen here is that this piece of the boundary, say lying along LK, comes here and just shrinks away, and you get a polymorphic curve intersecting the knot at one point, right? So basically, you get the curve with point condition in the boundary, and these things are like string operations counting such things. If you have a one-dimensional chain of strings in S3 and it's moving, then at some kind of points it will hit the knot, and there you split it in two. So this is this operation. One is one and one is the other, because, you know, they can also be now. But there can, of course, also this can happen the other way around, right? So it can shrink along N, or it can shrink along LK.
Could you write the chain complex, like the vector space underlying this chain?
Yeah, I could, but I won't. So in order to do this, I would have to enter actually into the discussion of what. So what we proved was just only in degree zero. But the chain complex would be, you take chains of paths beginning and ending on the knot, and then you have to take tensors of those, right? Because you would like to, in the chain complex, to have something mimicking this algebra. So that's what it is. So say somehow it's chains on the path space, the space of paths connecting the knot to itself. But then you have to make that into like looking like a DJ.
So the del S3 operation maybe is easier to see, at least to me, where you sort of take a chain and you intersect it with the locus where the chain passes through K at another point,
Yes.
and then you cut it up into two sub-chains.
That's right. That's exactly what it is.
And what's the del LK?
That's the same thing, but so basically you're if you think about it, it's the string topology of a singular space which has one S3 piece and one S1 times R2 piece, and then you have to say what's going on along the singular locus. And then the chain can pass, you know, it can pass in S3 through the knot, or it can pass in the other one through the, so they're completely symmetric in some sense. Yeah. But then, so this first relation, sorry for saying all this, but this first relation is exactly related to what happens when you're, you know, this is your knot, and then you see a little string that then goes off along this disappearing. So that's exactly it, somehow this boundary operator there, and the other one is when there is a little guy in the conormal disappearing. So those are the relations. And this is somehow useful to people knowing things about the fundamental group. So there is also a slightly more non-commutative version of this, which tells you that the non-contact homology knows, in this non-commutative version, a lot about knots. But let me not go there, but let me instead go here. So now, what one can check is that if you have a representation of the fundamental group into GLN, which has the following form on the meridian and longitude, so you know they commute, so you can diagonalize them simultaneously. So then, in fact, by just checking now these relations, you find that e to the x not e to the p naught lies in the augmentation branch. So it's a somehow simple thing. You just have to check this. And oops, I'm sorry. Yeah. So this one is has one eigenvalue equal to p naught. It's like the A polynomial, but with bigger matrices.
Why is there an asymmetry between what you're asking in one direction and the other? I mean, the one you asked it to be, in the U1 start, and the other one you allowed arbitrary freedom in the other conditions.
Yeah, but, I mean, I can normalize it so that it's like, if I choose the right. I mean, I could go the other way around if you want to, right? I mean, I think. So I guess this is the not completely symmetric thing, right? Okay. So maybe I should. So instead of since I'm kind of rushing a little bit as always. So I should say that there is a very nice paper where this is explained slowly and nicely by Lenin. It's called the Topological Introduction to Knot Compact Homology. So there this is very nicely explained. So let me maybe refer to there. What I'd like to say here is that if you play with this formula a little bit, and you take an SU2 representation, then you find that in fact the A polynomial, which if you have an SU2 representation, you take the two coefficients and they give you an algebraic curve. And here, if you change variables a little bit, you find that actually the A polynomial divides the augmentation polynomial, and so that already by known properties of the A polynomial tells you that, say, this detects the unknown, right? Now, in fact, it turns out that all the augmentations in this Q equals 1 case comes from such GLN representation. So in some sense, we understand the entire thing from point of view of the knot complement, if you wish. Okay. So now, let me move to the non-exact fillings. And as we described before, we can now shift the conormal off of the zero section. So we fix that filling and shift it off, and take it into the conifold. And we try to follow our previous definition for an augmentation. So we'd like to have the non-compact, the non-exact Lagrangians also to define augmentation. So this is at least the kind of problem. So we as first approximation, we try to define the augmentation by counting such disks. But now, as kind of everybody knows, you cannot do it anymore. So there are new boundaries in the moduli space. Before, the exactness conditions guarantees that there forms no holomorphic curves on the Lagrangian LK itself. But now, it will. And And so what can happen is indeed when you look at the boundary of this one-dimensional moduli space that you see bubbling of a holomorphic disk, and therefore we don't have d squared, d epsilon or d equals 0. But following Fukaya and co-authors, we can try to solve this problem by using bounding cochains. They're called non-Lagrangian bounding chains, I guess. And how would we do that? So imagine that we have a nice perturbation scheme, so that actually we can look at the holomorphic disks on LK as just being actual disks sitting there. And then what we do, so normally in such situations you would like the evaluation map from the moduli space into the Lagrangian to actually bound, right? And then you pick a bounding chain and then you can resolve the problem. Now here they won't bound, so they at least not all of them. So they will go around the x variable, the homology of the S1. But in some sense they bound, their homology comes from infinity. So what we do is we pick some sort of bounding chain which carries the boundary sitting inside, so this is the boundary of D, and then the chain goes off to infinity as shown, and at infinity it follows some kind of standard curve psi in the class e to the x. So we somehow uniformize it so that it looks standard multiple of this base curve psi at infinity. And now,
So you're actually thinking of the filling by S3 minus K, that's why the class at infinity is this one.
no, I'm thinking about LK right now.
Oh, LK.
So it's the longitude class that survives. Meridian is key. So P is key. Okay, so that's what it's supposed to look like. So you could do
So it's not a mystery disk, I mean, you know what the holomorphic disks are.
At where? No, here. Or,
Yeah, I mean,
yeah.
you constructed a Lagrangian by explicit push off.
Yes. But I don't know any. I don't know the disks, I guess. I mean, I know them through asymptotics of this colored Homfley thing, right? But the disks I'm now looking at, so I'm looking at the holomorphic disks forming on LK inside the conical. So it's some kind of open Gromov-Witten disk potential, which a priori I don't know. And hardly know how to define, but anyway, there they are. Right. And now we can follow this idea of Gaius and others that that now we actually the formerly bad point which arises here now becomes a good point. So at the cost of counting not just the usual holomorphic curves, but holomorphic curves with somehow insertions of these bounding cochains. So basically at this moment, I don't really know where to go when I did split off like that. But now I have the cochain, the chain going off to infinity. So I decide that I go in the direction where the boundary now lies in the chain. Right? And then I continue like that. So that removes, for me, if I now pick these from all the disks, that would remove for me the bad boundary splittings. And now I can try again to define my chain map as before. And let's see what happens. So what happens is that I basically have no. I have to look at the boundary, so the boundary picture is already here. I have to look at the boundary of the one-dimensional moduli space, and there are two things that I, of course, cannot guarantee when I do this. So one is that the insertions all lie in the compact part. That's where I use them first. Of course, I cannot say that. So they can move to infinity. But what I want to claim is that in infinity, the insertions are very easy to control, because at infinity, remember, all the bounding chains, they look like a multiple of this fixed curve which I erased. Right? So they're just kind of the multiples of my base curve psi. So it's very easy to see, if I know these disks which I know from before, how many times, I count the things with insertions. This is easy. So, so the other thing that one needs to see here is that I cannot just pretend that I insert, so this is this configuration here, that I insert disks with bounding cochains, right? Because, if you think about something like this, which is about to break in two places, right? I cannot assure that this one breaks before that one or something like that. So I have to count not just the disks forming on the Lagrangian, but rather all configurations of disks that themselves are, insertions of some other things. So if you look at it, it will be some kind of count of trees where I have disks, my disks that I count in perturbation scheme at vertices, and then here there's some kind of intersection number depending on the chains that I pick. Right? So some kind of linking things over here. So the Gromov-Witten disk potential is not the naive count that you would get. You have to take into account this obstruction chain. But then, once I do that, and so then this will be a chain map. And now let's see what this amounts to if I count things correct. So, well, what it amounts to is I have to figure out how many times or what happens with these insertions. But that's kind of easy to see, right? So up here, the Gromov potential was something like some numbers, and then e to the kx ql, right? But up here, they all look like multiples of disk size. So if I have my disk, which up here looks somewhat like that, and I have to count how many times can I insert, I just have to see how many times does it intersect this curve. And that's just keeping track of how many p turns I do, right? And if you think about it, then the count is exactly e to the dw dx of k, right? So basically, I can insert. So first I can insert nothing, right? That's the one. And then I can insert things. So why this? Because if I go k times around, I can insert it k times in p, right? So the derivative is k ck. Right? So if I go k times, I can insert k times. And now I can insert it once, or I can insert twice, right? If I have two intersection points, and that's exactly this w dx squared, but then I have to divide by the symmetry, because I can do it one way or other way, and so on. So you see that this counting, this insertion exactly corresponds to this substitution. So therefore we see that if I substitute p as the w dx in then I have a branch of the augmentation right. So that's relating the two things. Right? Good. So that's the conclusion. And now that's maybe, and this also I said, so somehow you see here that this Gromov-Witten disk potential needs to be a little bit modified from just counting disks. And I think that if you think about yesterday, for a little bit, then I was saying that, in terms of this topological string, the path integral localizes on the space of holomorphic curves, but now the moduli space is a space with boundary. And I think this kind of linking business and trees, that's exactly is the boundary term. So you need to take care of it somehow, and I think this is how it arises from physics perspective. Okay. Yeah, let's maybe not talk too much about links, but I want to cover one more thing we can come back with. But now, what's more to prove in some sense from this physics relation? So the point is that the augmentation variety in general, for I think already for before, is not irreducible variety. So if it was irreducible variety, you get the branch, you sort of have the whole thing.
Didn't you say there's an e to the p minus 1 and e to the x minus 1?
For q equals 1. So in general, you get the branch of this variety, but you don't get all of it in some sense this way. So what one would like is to have other Lagrangian fillings to cover, in some sense, all of the augmentation variety. And I think it's too much to ask. So, you know, if you think about, for example, you would like to have something corresponding to the knot complement sometimes. Knot complement fillings cannot generally be shifted off, right? For fiber knots you can do it, but
Do we know?
I don't know, but I definitely know, I don't know that they can be shifted off. I think there is some obstruction. I don't know it, but I think there is. I think for fiber knots you can do it probably. I mean, if you find this, at least if you, I think you would find some one form, right?
Yes.
And that is almost fiber, right? So maybe you know it. I don't know, but anyway, so maybe not even these two are enough, right? So maybe you need more. So one would like to have probably some kind of generation criterion and finding that you can find Lagrangians for everything you need to cover the whole curve. So these I don't know how to do, but I think this is a very interesting problem, and also to develop this a little bit in this setting with obstructions going off to infinity and so maybe it's not so difficult, but not so different from what's in other situations, but I think this is kind of a problem. Okay, so now I have a very short time remaining, but let me anyway start, and I will continue probably tomorrow with this. But let's now take a look at other manifolds. So in particular we look at another class of two wide manifolds, so kind of geometric quotients of S3. So for those, there are counterparts of the conifold. So basically, of course, you can do the same thing that we did from the start. You can take the T star S3 and you can collapse the zero section and try to grow something out. And here, in the constructions one has exactly one scalar parameter for each free homotopy class of loops. So if you think about this story, if we want to carry it over, then what would be the, if you, so knot contact homology somehow you can still do. And if you think of this thing carried over, then the Gromov-Witten least potential would be a function of much more variables. Right? And just to kind of finish, and then we'll discuss this with more details tomorrow, what one might wonder is what happens on the knot contact homology side, and what happens is that you need to view the knot contact homology, which is the Legendre algebra, not just it's interesting, but not so interesting. I'm sorry. Let's see. Yeah, so here, last remark. So I'll come back to this tomorrow. So now here we cannot forget about all the Ray orbits. And so the knot contact homology algebra needs to be considered as an algebra over the orbit algebra. So you can have splittings down to orbits. And it turns out that if you compute the degree 0 part of this algebra, then you get exactly free algebra, you know, commutative thing on the free homotopy classes. So it matches, right? So there should be a counterpart of all these for other manifolds. But I will leave that till beginning of the talk tomorrow. So, thank you very much.
Any questions, comments?
Do you believe the theory exists for things that aren't quotients of X3?
I mean, I don't know, really. I think it should be a little bit difficult. So, in particular, if you believe, I mean, there are manifolds, like if you take RP3, connect some RP3. You have quite a lot of homotopy classes. so at least, I don't know, it wouldn't be a compact manifold. So I don't know what to believe. But at least it shouldn't be simple.
Yes. I missed what you said in the previous slide about the XN. Can you say something about what the XN is?
Which XN? For
The the caviar, the first one,
For RP3 or for any?
for another thing.
Yeah, for RP3 it's a local T1 times Q. So I'll tell you, you can see if you take RP3 and you put it in CP3. And then you take a purely imaginary column. Right? And then it doesn't kind of intersect, so you take the neighborhood and go the other way. But okay, so okay, I'll talk about this tomorrow.
Focusing on complex numbers, there's open terms, there are no exact things here, but things are even in many pieces. And this function about it.
I mean, I cannot prove it directly, but somehow, if we believe these things, then you have a direct equation, right, for the augmentation polynomial. So when you solve for one variable in terms of the other one, you get a nice analytical expression. So it should converge, whatever we do. So somehow,
So you don't need to introduce notebooking.
right, in some sense I don't need, but of course I would need to do it if I really define it. But somehow, whatever definition you have, it should fulfill this. So it will be analytical.
Okay. Okay, let's thank Tobias again.